Good afternoon. Today we're going to start talking about the hypothalamus and the role that the hypothalamus plays in regulating our autonomic function and some of our homeostatic functions. And so a large part of today's lecture will also fall under the category of endocrinology because a lot of what the hypothalamus does, it does with the pituitary glands, which secretes hormones that regulate many of our homeostatic body functions. And so a good place to begin is probably just a general kind of picture of the anatomy of the structures that are relevant to today's lecture. And so kind of to point out, begin with, the hypothalamus is right here, and the hypothalamus is connected to the pituitary gland by way of the infundibulum. And so you don't see the pituitary gland here, but you do see the pituitary stalk. And be appreciative of the fact that the optic tract is very close. The optic chiasm is very, very close to the pituitary gland here. This would be the mammillary bodies. Here is the internal capsule. So these are all the fibers that are coming from the cortex going down into the brainstem. This area right here would be the cerebral peduncle. This would be the red nucleus here. This would be the aqueduct here. Okay? And so we have the lateral geniculate nucleus, which is the relay nucleus for vision. And we have the medial geniculate nucleus, which is the relay nucleus for auditory. This area here is the temporal lobe. In particular, this is the uncus, and inside the uncus, this is the amygdala. And so this is also involved in some of the structures that we're going to be talking about today. So it's a pretty busy structure anatomically. So this is what it looks like from the ventral aspect of the brainstem. If we do a sagittal section, the area of interest is going to be this area right here. So this is the hypothalamus. This, of course, up here would be the thalamus. Okay, and we are also looking at the fornix, which we'll kind of talk about a little bit today, but a lot tomorrow, or a lot on Tuesday. The mesencephalon, the third nerve here, pons, medulla, and so on. So really we're going to kind of focus in on these nuclei right here, the infundibulum and the pituitary gland. Now remember that the pituitary gland, where does it sit? It sits in the sella turcica, so you basically don't ever see that when you look at a fresh brain dissection. So I try to simplify the structures that you need to know on this diagram, and so it kind of breaks down into 6 big areas: the preoptic area, the supraoptic area, the tubercle area, which is around the stalk, the mammillary area, which is around the mammillary bodies, and then there's a posterior and lateral part to the hypothalamus. And we know that each of these nuclei are important because they participate in producing releasing factors that play on the pituitary gland that release the hormones that regulate a lot of our bodily function. And so we'll be talking about the various nuclei, that are related to those big 6 areas in the hypothalamus. This is a more anatomically correct representation of the location of the nuclei, and I'll point out to you again that we have the pituitary gland, right here. We have the infundibulum here, and then these are all the nuclei of the hypothalamus. It's also important to kind of remember that the optic chiasm is very close to this, so the optic chiasm, the optic nerve, are a lot of times involved in pathology that affects the hypothalamus and the pituitary. Okay, so the way this works is there are 2 big subdivisions of the pituitary. There's an anterior pituitary, which is connected to the hypothalamus by a vascular portal network. And then there's a posterior pituitary, which is directly connected to the hypothalamus through neurological connections, and we kind of consider that the neurohypophyseal part of the hypothalamic pituitary system. And so the way, again, that this kind of works is that there are nuclei up here in the hypothalamus. So these are those nuclei that we just talked about, and they have neurons that come down into this infundibular part of the pituitary hypophyseal axis, and they actually produce releasing factors which are carried into the pituitary, the anterior part of the pituitary, and then these releasing factors, which are neuroendocrine substances, they then play upon the anterior hypothalamus to then release the hormones into the general circulation. And so these hormones then go out and target distant organs. The posterior pituitary, on the other hand, has this direct connection with the nuclei where the neurosecreted hormones are actually released directly into the neurohypophyseal posterior part of the pituitary gland. So the anterior pituitary is connected to the hypothalamus by virtue of this vascular portal network, and the posterior hypothalamus is directly receiving these neuroendocrines that come from the hypothalamus directly. Okay, so there's a difference between the anterior and posterior pituitary function. And so we kind of divide it into those two big categories. So the first one we're going to look at are the anterior pituitary hormones and releasing factors. And so the areas that are important here are the anterior hypothalamic nucleus, which releases follicle-stimulating hormone, the preoptic area, which releases luteinizing hormone, the dorsal medial hypothalamus, which releases prolactin. Anterior hypothalamus also releases adrenocorticotropic hormone and thyroid-stimulating hormone. And the arcuate nucleus of the hypothalamus releases growth hormone. Now, some of these are, pretty self-explanatory. So, growth hormone is responsible for targeting your bones, your muscles, everything that you kind of grow as you grow into adulthood. And so that's growth hormone. Some of the others are maybe a little less intuitive. The follicle-stimulating hormone and luteinizing hormone are both actually released by a gonadotropin releasing factor, which is in the hypothalamus. And the follicle-stimulating hormone basically kind of prepares the developing eggs in the ovary to come to the point where you ovulate. And so we know that there's a pretty much the same for all women. There's pretty much the same kind of a picture here as to what happens to FSH during the menstrual cycle. And so again, follicle stimulating hormone is very important for the development of the egg, and then luteinizing hormone actually is released in a very big pulse at ovulation, and this actually causes ovulation and then the luteinization of the remaining structures. So these have to all happen in very close timing. And in fact, there are a lot of different assay kits that women can use to be able to actually detect exactly when ovulation is about to occur, simply by analyzing the LH that's in the urine. And so there are a number of commercial products that do that. So it turns out that FSH and LH are also very important in men. So the FSH is very important for spermatogenesis in men, and luteinizing hormone is very much responsible for producing testosterone. And so they have a little different role in men and women, but very important, very important for reproduction. Prolactin is the hormone which is released by the pituitary that makes the breast develop. And in pregnancy, when you have high estrogen, it actually makes the breast get ready to actually lactate. And so the prolactin prepares the breast, for breastfeeding upon delivery. Prolactin is also very active, or can be very active. It's men have it too. They just have a little bit less. If you take a man and give him the same levels as a woman, his breasts get big just like a woman. So basically, it's breast development. ACTH, adrenocorticotropic hormone, is important. This is a hormone which is secreted by the pituitary that plays upon or targets the adrenal gland, and it causes the release of glucocorticoids from the adrenal gland. So ACTH is the hormone which targets the adrenal gland to produce steroid-like substances. And we know actually that there's a diurnal variation. We know that ACTH levels change in response to stress, for example. And so it's actually involved in the immunological system also. Thyroid stimulating hormone is a hormone which targets the thyroid gland. TSH causes the release of T3 and T4 thyroxine from the thyroid gland, and the thyroxine then targets every organ in your body and establishes what's called the basal metabolic rate. So it's kind of responsible for regulating the rate of metabolism in your whole body. Any questions about the anterior pituitary hormones? So this is another diagram that kind of shows the releasing factors coming from the hypothalamus, going into the portal system, targeting the anterior pituitary, and then releasing, the growth hormone, the ACTH, the FSH, LH, growth hormone, and prolactin. Any questions? Okay. So, as you might imagine, there are a number of things that can and do go wrong. These are actually beautiful feedback systems. Last time we talked about negative feedback control, and so your hypothalamus is kind of like this computer, and the computer is all the time sensing the levels of your hormones, and it is adjusting how much releasing factor that you need in order to maintain a set point. And so there, as you can imagine, in something that's very delicate and very, very well tuned like that, there are a number of things that can go wrong. First one we're going to look at is a disease called Cushing's disease. Have y'all ever known somebody that had Cushing's disease? Okay. Cushing's disease in most people produces what's called Cushing's syndrome. Now you can also get Cushing's syndrome from just taking exogenous prednisone or cortisone. And so have y'all known somebody maybe that took steroids, took cortisone or prednisone? Maybe somebody that had really bad arthritis or lupus okay. So some people have to take steroids typically to suppress inflammation. So there's a whole array of immunologically mediated disease where patients take steroids, and it'll produce the Cushing syndrome. And this particular case that we're looking at first is where the pituitary gland produces too much ACTH. So if you produce too much adrenocorticotropic hormone, you're going to produce too much what? You're going to produce too much glucocorticoid. You're going to produce too much circulating cortisol basically you're going to produce too much of the glucocorticoids, the things that are like prednisone and cortisone. And so what do you get? So if somebody that either takes exogenous too much steroids, or somebody that has this, say a tumor in the pituitary gland that secretes ACTH, is going to have weight gain. It'll increase the blood pressure. It actually affects your memory. It changes your short-term memory. It may make you irritable, or it may actually make you give a sense of feeling good. A lot of times people that have this actually have a kind of a feeling of feeling really good. It can make hair grow places where it shouldn't grow. Women in particular will get hair on their face, a lot of hair on their face. It can change your immunological function. Basically, it immunosuppresses you. And actually, one of the characteristic features that I look at is what's called the buffalo hump. So somebody that has either it's taking too much steroids or has Cushing's will actually develop a great big hump on the back of their neck. And so they get kind of like a buffalo hump right on the very back of the neck, right in that place there. And so how do you treat this problem? Well, first you have to recognize it. So if you have this constellation of symptoms, you become suspicious. Okay? And the first question you ask is, if you see somebody that has Cushing's syndrome, you ask them if they're taking steroids, because, that can produce all of these things. And if they're not, well then you have to become suspicious that there might be a secretory tumor in the pituitary gland which is producing too much ACTH and is causing this constellation of symptoms. Okay? Now, do I take it that nobody in this class has ever taken cortisone or prednisone? Is that right? No, nobody's ever taken either one of them? You have?
I've taken it.
Yeah? For what?
I have like really bad reactions to fire ant bites.
Okay, so it was because of allergy reaction kind of thing?
Inflammation.
So, inflammation. Anybody else? Okay. Well, these are real common drugs. They're used a lot. What happens if you take steroids? If I give you 30 milligrams of prednisone, and you take it for a month, what happens to the ACTH level in your brain? It goes down. That's right. Why?
It gets used to you supplying it instead of making it.
Yeah. So basically, it's feedback loop, and so that's actually how we tell. Because one of the other things that can happen is you can get a tumor in your adrenal gland. So just like taking too much prednisone, if you have a tumor in your adrenal gland that secretes glucocorticoids, you can get the Cushing syndrome, okay? But when you actually do a blood test for a secreting tumor in the adrenal gland, you find what? The ACTH level is what? This is an exogenous tumor that's secreting too much steroids in the adrenal gland. This is not Cushing's syndrome or Cushing's disease. It would be low, okay, because the tumor now is making the glucocorticoids. Your pituitary is normal in this particular circumstance, and so you do an ACTH level and you find out that it's low. Okay, that pretty much tells you, and you have the symptoms of Cushing's disease, Cushing's syndrome, excuse me. You would then suspect that you probably have an adrenal tumor, not a pituitary tumor. So by looking at the ACTH level, you can actually tell where you have to focus your attention, as to what might be causing the problem. Okay. Yeah, while I'm thinking about it, let me go back. We were talking about FSH and LH, follicle stimulating hormone. So, in a woman who is perimenopausal or just going into menopause, Okay, what happens to the FSH level? How do you diagnose? You can diagnose menopause by looking at the FSH level. If a woman is going into menopause, okay, she's no longer making her ovaries out of eggs, she can't make the estradiol, okay? And so what happens? The pituitary gland is saying, hey, kick the ovary harder. You know, let's try to make it, you know, produce some more eggs. Okay, so FSH level goes way out the roof. You know, ordinarily FSH is maybe 10 or 15 international units. In a menopausal lady, FSH is 60 to 100. And so that's the way actually that, you know, you can do an infertility screen. Sometimes, you know, you can have primary ovarian failure. If you have primary ovarian failure, you know, as a cause of infertility, well, your FSH level is going to be astronomical. It's going to be very high. Okay, so that's how you use these. You can, you know, there are blood tests for these hormones. Okay. Yeah.
So for a menopausal woman, does it just stay high the rest of their life, or does it like
stays high the rest of their life? Right. Yeah. And so actually, that's one of the criteria for in vitro fertilization. So you have an infertile couple. One of the first tests that you do, or you know, you do a bunch of tests, but on the woman, one of the first tests you do is you look at the FSH level, because if the FSH is, you know, 40 or 50, she's not producing any eggs, and you can't harvest any. Any other questions? Now, just the opposite to Cushing's is Addison's disease. Addison's disease is almost always caused by primary failure of the adrenal gland. And in this case, you have too little endogenous glucocorticoids and mineralocorticoids. So basically, it's kind of just the opposite. You lose weight, your blood pressure goes down, you actually get hyperpigmented, you may have nausea and vomiting and diarrhea, and you become hyponatremic and hyperkalemic, and it can cause death. So somebody that comes in that has sudden or over a period of 3 months that has weight loss and says, gee, you know, I've gotten a lot darker, I mean, blood pressure is 100/40, and you know, they're very fatigued, and you do some couple of blood tests, you know, you can probably tell that they may have Addison's disease. And usually this is, again, caused by primary failure of the adrenal gland. How about thyroid disease? Anybody here known somebody who had thyroid problems? Yeah.
My mom does.
And she takes?
I'm not quite sure what she takes, but she had her thyroid removed like this year.
Okay.
Yeah.
Yeah.
My dad had thyroid cancer, but it didn't really seem to do any harm.
Good. So did he have the cancer removed?
I don't know.
What?
I don't know what happened.
You don't know what happened. Was he still alive?
Yeah, he's fine.
He's good. All right. So where's your thyroid gland?
Right here.
Right here, right in that little notch right there. That's your thyroid gland. And so somebody that has a thyroid tumor or a goiter, you know, the thyroid gets big. You can actually palpate your own thyroid gland. It's right, that little notch there. That's your thyroid gland. Yeah, so I mean, it looks like this is a very popular disease. I saw about half the class raise their hand. And so thyroid problems are quite common. Yeah.
How does iodine prevent thyroid problems?
How does iodine?
Is it iodine or fluorine? I don't remember.
So, yeah, wait a minute. Wait. Back up for a second. So the thyroid, the thyroxine, the T3 and T4 are iodinated proteins, okay? So if you get exposed to a nuclear bomb or, you know, a nuclear accident, the iodine gets into the milk of the cows, and you drink the cow's milk, and you get the iodine, and then that can cause problems in your thyroid. And I think what you're thinking is one of the ways you can treat thyroid toxicosis, in other words, a toxic goiter, is to give somebody radioactive iodine. You don't actually have to do a cutting surgery, but you can effectively kill the thyroid gland by just drinking a glass of radioactive iodine, which then goes almost all to your thyroid gland, and it kills the thyroid gland. That's a common way to. Anybody had that happen or know that story?
I've heard something about iodized salt.
It's what?
Iodized salt.
Yeah, if you want to make more thyroid hormone, you eat salty fish and have iodized salt. That's right.
Okay.
That's healthy for your thyroid gland. Okay, so somebody that has a toxic goiter, somebody has a thyroid tumor, okay, that you can tell because they get really, really nervous. I mean, they start shaking and they're irritable and heart rate's up, their temperature's above 37 C, they perspire a lot, usually lose weight, and they have trouble sleeping. So that's the symptoms of hyperthyroidism. Symptoms of hyperthyroidism. So if I have a thyroid tumor that is secreting thyroid hormone, there's two, there's T3 and T4, thyroxine. If I have a thyroid tumor that's secreting too much thyroid hormone, what happens to the TSH level? It what?
Wouldn't it drop?
That's right. You're right. Andre, you're right. Don't be apologetic. If you have too much thyroid hormone, your hypothalamus senses it, it measures it says, wow, I got way too much, my thyroid's working too much, cut down on the TSH. And so the way you diagnose it, at least partially, is to look at the TSH level, which you can just get a blood test, you can get the results back in an hour or two, and it tells you that something's not right. And so that's the way you would treat a hyperthyroid. Now there's another problem that's probably even more common, and that's hypothyroidism. And about 10% of the population at one point or another in your life actually gets hypothyroid symptoms. And so the symptoms of hypothyroidism are cold intolerance, weight gain, generalized fatigue. You're all the time tired, and you have trouble with concentration and memory. Y'all had any of those symptoms? Maybe you're hypothyroid. Probably not. Okay. And so if you're hypothyroid, because the thyroid gland now is not making enough thyroid hormone, what is your TSH level going to be?
It's going to be high.
It's going to be very high. That's right. That's actually how you diagnose it. And so if you're hypothyroid, you can take thyroid hormone, you can take replacement hormone. So basically there's a little pill you can take. And you can then monitor the TSH level to get the thyroid back into balance, so your BMR is kind of more what it should be. Yeah.
What about goiters?
A goiter.
How does that happen, and what do you do with it? Do you just leave it alone?
Sure, that's a good question. And so you can get there's two ways you can get a goiter. What two ways? I'm going to pick on Kristen. That's right, Kristen?
Yeah.
All right, now I know your name, okay? I'm going to pick on you. So there are two ways you can get a goiter.
Do I know the two ways?
Yeah?
I have no idea.
Well, give it a stab. We just talked about one, thyroid tumor. Man, it gets big because you got a big old tumor. You can feel it in your neck. So one of the things when you go get a physical exam, if you ever go see the doctor, he'll probably feel your neck. He'll have you swallow. He'll say, Kristen, swallow. You feel when you swallow how your trachea kind of goes up and down. You can kind of feel the thyroid gland go underneath your finger. Okay, so one way you can get a tumor in the thyroid gland. How else can you get a goiter? Yeah.
Iodine deficiency?
Iodine deficiency probably is going to produce hypothyroidism. And a goiter we usually associate with hyperthyroidism. So too much iodine, too little production of the thyroxine, and so that's usually going to be hypothyroid. Now we're talking, the question I think Kristen asked was has to do with a goiter. You can palpate something in the neck. So tumor is one. The other way you can get a goiter is if you have a tumor in the pituitary gland. A pituitary tumor that produces too much TSH and no longer is actually looking at the thyroid level is going to kick the thyroid gland, until it can't produce any more. So it's going to make the thyroid gland swell, and it's going to produce a goiter too. So there's two different ways you can get a goiter. Yeah. That answer your question?
What happens then?
Oh, what happens if you get a
see
goiter?
People with like huge ones,
Yeah.
and they're just like hanging out, like
Yeah.
they don't do. I don't know.
Yeah, so you can get, this can get big. What else happens if you become thyrotoxic? Have you ever seen somebody that has Graves' disease? This is actually a good word for y'all to learn, since y'all can blame Kristen for this. Graves' disease is a disease that's produced by a tumor in the thyroid gland, typically producing a goiter. Okay? And these tumors in the thyroid gland a lot of times produce some kind of weird proteins. Okay? They're not all just T3. And these proteins in Graves' disease, they actually target the muscles in the eye. And somebody that has Graves' disease has these really protruding eyes, big, spooky Halloween-like eyes, where it looks like the eyes are about to pop out of the socket. Okay? You know what I'm talking about? You don't. Have you ever seen somebody who has Graves'?
My aunt did.
Your aunt did.
Yeah.
Yeah. And actually that's caused by an antibody to a protein that the thyroid makes that cross-reacts with the muscle around the eye and causes the muscle to swell, becomes inflamed. It's weird. It's kind of a weird kind of thing. Anyway, it makes the eye protrude, and it can occlude the optic nerve and cause blindness if you're not careful. And so, you have to treat the underlying problem, which is the thyroid disease. And typically you treat the thyroid disease, the goiter and the eye problems, typically resolve. They go away. So Graves' disease is the ophthalmological complications of thyroid. It's also called thyroid eye disease, immunological thyroid eye disease. Okay, yes?
What causes hypothyroidism?
Hypothyroid. So hypothyroidism, about 10% of the population gets hypothyroid. Not enough iodine in the diet. That's one thing that can cause it. It's probably related to age. So as you get older, you're more likely to have, thyroid failure. But there's some juvenile forms, of hypothyroidism too. Okay. Okay, any other questions about the thyroid eye disease or thyroid? Okay, the neurohypophyseal function is divided really into two parts. One is the part which comes from the supraoptic nucleus, which secretes vasopressin, ADH, antidiuretic hormone, which targets the distal convoluted tubule in the kidney and facilitates reabsorption of water in the kidney. The paraventricular nucleus secretes oxytocin. So oxytocin is actually the releasing factor that actually releases milk from the ducts in the breast. And so prolactin develops the breast. Prolactin, makes the tissue be ready to lactate. But actually, it's the sucking on the nipple that produces a reflex arc. There's actually a neural arc which goes back up to the hypothalamus, which then releases oxytocin, and that releases the milk from the nipple. Okay? Got that, Andre?
Yeah, what was SO?
What?
I don't release milk, but what was SO?
Supraoptic nucleus. Have y'all ever heard of witch's milk? You ever heard that term? It's Halloween.
It's what the witches fed their little imps that help them perform all their magical.
The what now? Tell me again.
That and like so in England to like detect if there's a witch, they would find the third tit and like see if they poke it, if it like blood comes out, and that's what they thought like the witches would suckle their little imps and like little animals that would help them do magical things that were bad.
Really? Okay. That's a great explanation. About 5% of babies, so babies in the womb, they get exposed. What? They get exposed to prolactin, right? And the prolactin crosses the placenta. And so if you look at just a newborn baby, their breasts are big, right? And a lot of times, about 5% actually will have colostrum that will actually come out of the nipples. And that's called witch's milk. My story's not as good as yours. Okay, so oxytocin is the milk let down. Yes?
What did PV stand for?
Paraventricular nucleus. That goes back to that table I made you, the one that you have to memorize so you know what these things are. So anyway, but oxytocin does what else? Oxytocin is also
The pregnancy, the labor.
that is the hormone which produces productive labor, right? Exactly. That's oxytocin, pitocin. That's actually causes the uterus to contract. So ADH is secreted by the posterior pituitary, enters the bloodstream. It targets the distal convoluted tubule, which is this part right here, and it actually causes water to be reabsorbed back into the blood. Did you know if you don't have any ADH, that you actually produce, the kidney actually absorbs a large part of that in the proximal tubule. But if you have no ADH, you actually would produce about 18 liters of urine a day. Okay, that's called diabetes insipidus. So if you have a defect in the production of antidiuretic hormone, no ADH, you end up with polyuria. Basically, you're producing tons and tons of urine. Okay, and if you produce tons and tons of urine, what do you become? You're losing lots and lots of fluid, so you become hyper or hypoosmotic. You become hyperosmotic, exactly. And so this is diabetes. It's called diabetes insipidus, as opposed to diabetes mellitus, which is the more common, form of diabetes that we kind of think about. And I think I showed you this before, but this is kind of the diagram. It kind of shows how ADH plays on the kidney to regulate your osmotic pressure. So your brain is constantly monitoring the osmolarity of your blood, and it's causing fluctuations in the vasopressin to basically keep your blood osmolarity at about 300 milliosmoles. Okay? Any questions? So the hypothalamus is also very important in regulating your appetite. In fact, this is probably one of the reasons why, people maybe become obese. And so there are two nuclei that are important here, are the lateral hypothalamus and the ventral medial hypothalamus. And if you destroy the lateral hypothalamus, you become anorexic. And if you destroy the ventral medial hypothalamus, you become hyperphagic. You eat and basically eat all the time. Okay? And so how do you know that? Well, we can take an animal and we can lesion the medial or the lateral hypothalamus, and so we can produce either a kitty cat that looks like a raccoon, or we can make an emaciated little kitty cat. And so you can kind of see how your hypothalamus is looking at, amongst other things, your blood glucose level, and it's regulating your appetite, whether you want to eat or not eat. These same two nuclei are involved in the rage reflex. And so if you destroy the medial hypothalamus, you'll create a very angry and ugly cat. The hypothalamus also regulates temperature. The anterior hypothalamus is connected to the autonomic nervous system and can create either shiver, it creates sweating, or the posterior hypothalamus will make you shiver to increase temperature. And so the temperature regulation again starts in the hypothalamus. So your hypothalamus is reading, you know, the baseline temperature, comparing it to what the set point is, and it will, depending upon whether the temperature is too high or too low, the green pathway I think is showing where you want to actually gain weight, gain temperature by either shivering or constricting blood vessels, and the red pathway is just the opposite, where you dilate peripheral blood vessels and you try to maintain heat. So these are all regulated through the autonomic nervous system. Yes.
Is the fact that the areas that secrete the hormone that relate to like hunger and satisfaction, like that they also control rage? Is that why whenever someone's hungry, they tend to be angry?
Yeah, that's a good. I thought of that. Actually, I thought of that myself. I mean, that is a fact. You know, if you get really hungry, you get irritable, and I don't know. Maybe it is. Maybe it's the low blood sugar. I don't know. Something. Maybe they are related. Good thought. Okay. So anyway, your hypothalamus is regulating all kinds of very important functions. So it also, the hypothalamus is the head nucleus. You know, think of this as being the controlling nucleus for your autonomic nervous system. Okay. So your autonomic nervous system, we've kind of touched on it, but we're going to look at it in a little more detail, is the sympathetic nervous system and the parasympathetic nervous system. Parasympathetic is your kind of baseline, kind of homeostatic state, and then the sympathetic is the flight or fright. Basically, it's when you get scared. So sympathetic is response to obnoxious stimuli. And so your hypothalamus here is the head nucleus. It regulates. It's the one that is actually giving you information which regulates your parasympathetic nervous system and your sympathetic nervous system. Now, in terms of the organization of these two, the sympathetic nervous system, these are both two neuron pathways. The sympathetic nervous system has a very short preganglionic neuron and a very long postganglionic neuron. Just in contrast, the parasympathetic has a very long preganglionic neuron and a very short postganglionic neuron. Okay. Now, the neurotransmitter at the preganglionic for both parasympathetic and sympathetic, for both, the preganglionic is acetylcholine. Parasympathetic, the second order neuron, is going to be acetylcholine. But the sympathetic, the second order neuron, secretes norepinephrine, or if the target is adrenal, it'll secrete epinephrine. Okay? So that's the difference between the sympathetic and parasympathetic. Preganglionic, first neuron, the first synapse, acetylcholine. Sympathetic, second order, secretes norepinephrine or epinephrine. And then the parasympathetic is acetylcholine, acetylcholine. The parasympathetic nervous system is distributed throughout your face, your trunk, to a lesser extent in your extremities, but it goes everywhere. And this is distributed primarily through the vagus nerve. So your vagus nerve, there are branches that go, I think, with the 3rd, the 7th, and the 9th cranial nerve, but the vagus is the big one. That's this one right here, which goes to your heart, your lungs, your gut, your liver, go down into your sex organs. So basically the parasympathetic is all a system which is really kind of cranial nerve oriented, with the exception of a few sacral branches. Okay, parasympathetic, because this is a cranial nerve oriented kind of a system, there are a couple of these that you have to be aware of. First one we've talked about, I think, extensively, the oculomotor nerve, okay, has the branches which go to the eye. Actually, it originates in the Edinger-Westphal nucleus, and it goes to the ciliary muscle to cause you to accommodate to see it near, and it goes to constrict the pupil. So it's acetylcholine, just like we've talked about before. The seventh nerve we talked about, and the seventh nerve has the branch which goes to the what's called the greater superficial petrosal nerve, which goes to the lacrimal gland, and it produces tears. Okay, the cardi-tympani branch of the seventh cranial nerve goes to the submandibular gland, which produces some of the secretions for digestion in your mouth. So that's the greater superficial petrosal nerve and the cardi-tympani. The inferior olivary nucleus goes with the lesser petrosal nerve to the otic ganglion, which goes to the parotid, which is the major gland. This is the one that really, really is important for secretion in your mouth. The vagus nerve, we talked, again, you should go back and review this, but basically the vagus is going to slow the heart, basically constricts the bronchi. So it's if you stimulate the vagus nerve, you can produce a asthma attack. It stimulates peristalsis and it stimulates secretion. Basically, it promotes digestion in the gut. And then finally, the non-cranial nerve branches of the parasympathetic basically go down to the reproductive organs to create, basically is important for erection in a man, and it produces contraction in the bladder. Those are the important things there. Now, the sympathetic nervous system does just the opposite. Everything that I just said for the parasympathetic is just the opposite for the sympathetic nervous system. So just like where we had the vagus slowing the heart, the sympathetic also goes to the heart, but it'll speed the heart up. In the gut, it decreases your motility, it decreases gastric secretion. Basically it's the kind of the opposite of all the things that we just talked about. Now, the other thing that's interesting with the sympathetic, because it has a very short preganglionic neuron and a very long postganglionic neuron, the cell bodies, instead of being close to the target organ, are actually in a spinal cord organ which is parallel to the spinal cord. It's outside the dura, but basically it's the chain ganglia for the sympathetic nervous system, which is actually parallels, but it's outside the spinal cord. And that's where this first and second order neuron, this is the primary here, and this is all of these are secondary neurons that for the sympathetic nervous system. Okay, so it's it's pretty easy to understand. I think we covered most of those things. So the head and neck is a little bit different. So in the head and neck, the actual fibers that actually go out to the eye, here is the Edinger-Westphal nucleus, which is in the mesencephalon. Here is the superior and inferior colliculi here, superior and inferior colliculus. And so this branch is coming out to the ciliary ganglia, which is right behind the eye, which then sends fibers into the eye that then secrete the acetylcholine. That's actually pretty simple. Now the sympathetic is a lot more difficult, because the sympathetic actually comes from the superior colliculus all the way down into the cervical cord, into the intermediate lateral part. Actually, they go down into the even the low cervical upper thoracic cord, and then the sympathetics come all the way back up, and then they go to the eye. And so the third nerve is going to constrict the pupil, okay, but the sympathetics will dilate. So you've got these two systems that are kind of working in parallel. Now the reason this is important, and the reason that I bring this up for this class, is because there's a very important syndrome which is called Horner's syndrome. Which is produced by a tumor in the upper lobe of the lung. So it's called a Pancoast tumor. It's a tumor in the upper lobe of the lung. And this tumor will press on the sympathetics, okay? And so if I lose the sympathetic tone on the pupil, what happens when I look at the two pupils? So in Horner's syndrome, the side that has the tumor will have a smaller or larger pupil.
It won't dilate, so it'll constrict.
It actually will still dilate and constrict, but the pupil, the steady state pupil, is going to be smaller because it does not have the adrenergic, the opposing adrenergic influence. And so the other thing that Horner's does is, because this is a an adrenergic system, it actually changes your eye color. And so you see somebody that has two different eye colors, okay, you get real suspicious that maybe they got something going on with maybe their sympathetic nervous system. Furthermore, if you see that the pupils aren't equal, and one pupil is smaller than the other, and you look and they basically have different eye color and smaller pupil, that could be Horner's syndrome. Okay. Just a kind of a diagnostic pearl. Anyway, blood pressure. So cardiac output is equal to heart rate times stroke volume. Okay, and your heart rate and heart rate is regulated by the vagus and the sympathetics, right? So we got that one. We already did that one. Contractility is related by your opposing, adrenergics and cholinergics. Blood volume, pretty much constant. But peripheral vascular resistance, excuse me, you can change very quickly. And peripheral vascular resistance, we know, is a function of the sympathetic and parasympathetic system. So if you stimulate the sympathetic system, it will cause a constriction of a lot of your arterioles, and actually it'll raise your blood pressure, and that's protective. If you're trying to run away from the lion, you want to knock your blood pressure up, right? You want to have all the cardiac output, and you want to be able to climb the tree faster than the big cat. On the other hand, it can be a bad thing if your baseline level is too high. Well, over a period of time, it'll cause heart disease and arterial sclerosis and some other issues. But anyway, the point to this I'm trying to make here is that this is all tied into the hypothalamus too, because the hypothalamus now is actually sending signals out on the vagus and the ninth cranial nerve down to the carotid body and the carotid sinus here. Okay, and the carotid sinus is a sensor that's actually regulating or kind of monitoring what your blood pressure is. Blood pressure ? And so it's sending all these signals back up the ninth nerve. Okay, and these end up going up into the hypothalamus. Here's your hypothalamus here, and then it's sending down some other signals then that go through the sympathetic, parasympathetics, that then go down and constrict or dilate the blood vessels to regulate the blood pressure. And so the hypothalamus is involved in just about every bodily function that you can kind of come up with. Any questions? Very, very important. So now, the hypothalamus is also very important in regulating sleep. Okay, so and you stop to think about it. Sleep is one of those things that it's kind of automatic. I mean, you kind of do it. You don't have to think much about it. It's kind of natural. And to kind of begin the story, let me tell you that there is a part of your brainstem which is called the reticular activating system. Reticular activating system. It goes from the pons all the way up to even above the mesencephalon. So basically it goes through the whole brainstem. And so the reticular activating system gets inputs from pain and temperature, proprioception, auditory, visual. It's all the things that keep you awake, okay? So if you just stop to think about it, any kind of stimulus that is capable of waking you up is going to feed into the reticular activating system, and that's going to give you an awake signal. It's going to wake your brain up, whether you want to or not. It's also true that if somebody is comatose because of bad traumatic brain injury, that if you stimulate them with loud noise or stimulate them with painful stimuli, you can actually arouse them for a short period of time. And that works through this reticular activating system. And there are a lot of people that have been, that die. They're on a ventilator, they're in a vegetative state, that actually the brain is actually quite normal, but because the reticular activating system can't wake the brain up, they're comatose and not able to be aroused. And there's also miraculous stories where people have been in a coma for like 2 years, and all of a sudden they wake up and they're normal again. And so it has to do with this reticular activating system waking our brain up. Okay? So we know that the bigger you are, you can just kind of look at the size from the mouse to possum to cat, dog, and then a human, and then eventually you go down to an elephant. It doesn't hardly ever sleep. As you get bigger and bigger and bigger, you probably need less and less sleep. On the average, we humans require about 8 hours, something like that. I don't know, do y'all get 8 hours of sleep, something like that? Maybe. Turns out that actually sleep is, yeah, you had a question? No. Sleep is actually very, very important. Fact is, you can't convert short-term memory into long-term memory without having very good sleep. Okay, so this is actually really, really important for you guys to pay attention to. So we know that this occurs at all ages of life. Child, adult like you is in the middle. Someone like me, maybe down on the bottom. Anyway, we all basically have these cycles where over an 8-hour period we go through various stages of sleep. So, we'll start off, a lot of times we'll start off going down very, very deep, okay? And then we'll almost wake up. We'll almost wake up. And we'll have what's called REM sleep, rapid eye movement sleep, and then we go down again, these cycles. And you measure these with electroencephalogram, so that you can go over, and if you want to get your sleep cycle analyzed, you can go over to St. David's. They have a very nice sleep analysis center, and you can spend a night there, and they'll draw a picture just like I drew for you here, where it shows your cycles, and there should be maybe 4 or 5 REM sleep cycles every night for most of us. And you should actually have at least part of your time sleeping down in stage 4, the very deep sleep. So the question comes up, why do we sleep? I mean, it's an important thing. We all do it. Spend at least a third of our life asleep. So, why do we do it? Well, if you don't sleep, you get skitsy, and if you go without enough sleep, you'll die. I mean, that's just also a fact. And so we know that it's important. Yeah.
I've heard that these REM cycles can be an hour and a half or so.
They can.
So if it's an hour and a half, is it better to take an hour and a half nap or a 2 hour and 15-minute nap?
Yeah, I think what you're talking about. So the REM. So when you look at rapid eye movement, if you actually look at this, rapid eye movement is really pretty short. It's measured in minutes, tens of minutes, but usually not an hour. Okay, but these cycles themselves, this cycle here has a period of maybe a whole hour, maybe 2 hours, right? And so, the question I think you're asking is it better to have very deep short cycles or very long not so deep cycles? Is that what?
Is it better to wake up when you're at the top of the peak, or?
Okay. Well, let's talk about that. So, yeah, that's a good question, and let me try to answer it this way. And so again, how we got that curve was to monitor your three things. We measured your electrooculogram, your electromyogram, and your electroencephalogram. Okay, and staging sleep is based upon the frequency in the electroencephalogram. Okay, so you take this signal here, which is a time signal. This is a signal which is a function of time, and you do the Fourier transform of it. So basically I do the Fourier transform of this time signal. Okay, and I come up with a picture which just shows the power spectral content, something like this, which now is like, this is now measured in hertz. This is like 1, 5, 10, 15 hertz, and this is power as a function of frequency. Okay, and so based upon which, if you look at the power spectral density function of the electroencephalogram, you basically pick the peak, and that tells you whether you're in stage 1, 2, 3, or 4. So it's based just upon frequency of the electroencephalogram. And so if you look, you know, when you're awake, you basically have very high frequency. So you start off, you know, somewhere over here. So this is awake, and then as you go down progressively lower and lower, the frequency, you know, here is decreasing. So this might be stage, you know, stage or not asleep, or maybe early stage 1, and then stage 4 is going to be way over here. Stage 4 is just, you know, very low, kind of delta waves. Okay. So I'm still trying to answer your question, and believe me, I'm still kind of circuitously getting back to it. And so now let's look at the electromyogram. So the electromyogram measures your basal tension in the muscles, right? And so you have, you know, a certain baseline here, energy. Actually, you get a little more energy in 2, a little more in 3, maybe a little less in 4. And the EMG goes absolutely flat. You're absolutely paralyzed when you're in REM sleep. REM sleep is characterized by these rapid eye movements. You can see the saccades there. So we also know that during REM sleep is the time that you dream. This is when you know, are dreaming. And during the cycle of REM sleep, men will always get an erection. Now, I don't know what the equivalent is in women, but every time you guys, when we go into REM sleep, we're paralyzed, okay, and we have an erection. What do you think about that? Andre? Andre, do you ever have wild sexual fantasies while you're dreaming?
I think that's actually that's how they test whether or not someone's erectile dysfunction is.
Wait, Daniel?
That's how they test whether someone's erectile dysfunction is psychosomatic or if it's like an actual physical problem.
Right. Yeah, this is a way you can test it. Yeah, absolutely.
There was a movie in the 70s that talked about it.
Yeah, this is one way you can test it.
I have a question. So that thing where people like wake up, is that in REM sleep where you kind of wake up but you feel really paralyzed?
That's right. Have you ever been, you know, really asleep and somebody slams the door or an alarm goes off and you're just lying there and you just feel paralyzed? Right. Now, if you're a guy, you know, you got a boner, but I don't know about Okay, so you're lying there paralyzed, okay? And that's exactly what happens. That's during REM sleep. And you know, the times when you remember dreams is when you get awakened during the REM sleep. Okay? You don't remember all the dreams. You only remember the last one, or the one that was right before you woke up. Okay? So do you dream in color?
In first. Yeah.
It's not a trick question.
Yes.
You dream in color, okay? What do you dream about? Good things, bad things?
They're usually
Oh,
like,
you ever have a dream that's really scary? It's Halloween, somebody's chasing you with a knife or something?
Yeah.
I get dreams like once where I wake up and I feel paralyzed. I get those a lot.
Terror?
They're always like
Terror
bad dreams. They're always like
dreams, you know?
horrible, yeah.
That's probably why you're paralyzed, because when you're going through this dreaming, you have all these kind of weird thoughts and things. So I mean, you could commit a bad crime, maybe. Actually, that's been a defense for some murder. They were actually sleepwalking, or you realize that is a defense. But if you're really asleep, and if you're doing REM sleep and you're dreaming, you're paralyzed. And that probably protects you so that you don't do something silly, like jump out the window or something like that. And so dreams, turns out, are very, very important. They're very, very important in memory consolidation. But they also tell you a lot about you. Did you know that that's one of the main things that a psychiatrist, if you're going to get psychoanalyzed, that they'll want to know, want you to share dreams? Did you know that? Yeah, do you have a story you wanted to?
Oh, no. She's laughing at me because I have a dream journal.
You what?
I have a dream journal.
Do you really?
Yeah, I'm trying to train myself to remember my dreams.
You're training yourself to remember your dreams.
Yeah.
Do you remember any of them?
Some of them.
Yeah?
Yeah.
Like what?
Well, last night I really
Had what?
really had to pee.
In the bathroom,
Yeah.
okay.
Because I drank a whole glass of apple juice before I went to
Right
bed.
before you went to bed. That's probably not a good idea.
Yeah.
What's the response whenever, the dreams that you feel like you're falling, then suddenly your arm twitches?
Yeah.
And then, you're suddenly woken up.
Right, and that's right when you just wake up. That's when you're just coming out of REM sleep, and you can remember that dream. And you can train yourself to maybe remember your dreams so that you can kind of psychoanalyze yourself. But actually, when you're dreaming, your subconscious gets released, so you actually are playing out, fantasies and other things that you probably wouldn't think about in consciousness. Yeah.
Is there any connection between the reticular activating system and your dreams? Would you?
Yeah, we're going to talk about that in just a second.
Okay.
The pathway goes through the reticular activating system.
So sometimes when you feel like you're really scared, even though it's not actually happening, your body can't determine whether it's real or not.
Yeah, when you're dreaming, basically, so when you're dreaming, you're basically replaying a lot of the experiences that you've had. Typically, dreams have to do with things that happened to you in the last few days, okay, but they're not in any realistic context. So basically, you're allowing your brain to reinterpret all the sensory input that you had. And so the girlfriend that actually jilted you is now madly in love with you, and you basically, you're free to, your brain can fantasize whatever it wants. Yeah.
What about when you can control your dreams? Is that lucid dreaming? Are you still part of?
Have you ever tried to control your dreams? Have you ever been asleep and had a really good dream and say, man, I want to go back to sleep and I want to finish this one? Have you ever been able to do that?
I heard that if you don't move, if you don't move at all,
Yeah.
you go back to finishing that dream.
I've never been much successful in doing that. You had a question?
So if you realize during REM sleep, how does sleepwalking and sleep talking work?
Sure. So those are actually abnormal. We'll talk about that in a second. They're abnormal sleep states. Okay. Well, anyway, dreams and analysis of dreams. This is really, really interesting subject that I'm sure that y'all might have at least thought of. So what determines this? It's the reticular activating system. And in particular, it's the nucleus reticularis, pontus, oralis, and caudalis. So that's the answer to your question. Okay? And so what happens here is this is that nucleus, and it actually has an excitatory glutamate neuron which synapses on a glycine neuron, which then paralyzes the alpha motor neuron. That's how you get paralyzed. So basically, in the spinal cord, you get paralyzed by the glycine secreting neuron, which synapses on the alpha motor neuron. And so that is a part of that REM circuit. We also know that there is a master clock. So most of us, have a cycle where we get in a habit of going to sleep at a certain time and waking up at a certain time, which is actually a very good thing. If you get into a habit and you stay with that habit, it really makes you sleep a lot better. But we also know that the suprachiasmatic nucleus, which is just above the optic chiasm, and in fact receives a number of fibers from the optic chiasm, is very important in regulating your 24-hour sleep cycle. If you are blind, if you have no ability to perceive light, you do not have a 24-hour sleep cycle. You get all crazy kinds of sleep cycles. Not only that, you become infertile. So this is important in regulating the FSH-LH pathway. So exposure to really bright light, particularly in the morning, is very important in resetting your hypothalamus for reproductive functions and all your other hormone functions in addition to the sleep cycle. Okay? And so we also know that people that don't, that are depressed, if you are clinically depressed, you will probably have an abnormal sleep cycle. And so either if you're under stress or if you are depressed, you will not have that normal, REM cycle that we just looked at. So have y'all ever experienced any stress in your life? Nah, none of that. Okay. So why do we sleep? Well, we think that the non-REM sleep actually repairs membranes in our neurons. And for the REM sleep, we think that actually we reset our synapses so that they're kind of back at the baseline so we can start all over the next day. It's probably also important that we sleep so that we remove memories that really aren't important to us. Okay? And so this is a little diagram that kind of shows how with REM sleep, we're basically kind of resetting our synapses, and for non-REM sleep, we repair our biomolecular membranes that get damaged by the reactive oxygen species. And so this was taken from an article. I don't think I put the reference here, but this was from Scientific American last year. That kind of shows the blue line is maybe an important memory, one that you really should actually remember, and then the yellow part is maybe some other things that happen during your day that are kind of unimportant. And when you go to sleep, you actually erase the unimportant facts, the unimportant memories. And we think that this happens because during dreaming you replay the things that are important to you. So dreaming helps to actually reinforce the circuits that are important, and the others kind of get erased. And there's other evidence that, in fact, if you're not getting enough sleep, that actually your brain becomes hyperexcitable. I don't know if you've ever been sleep deprived and you get all kind of shaky, you kind of like this, and you react to things, quickly. Okay, that actually is a fact. We can document that. The number of synaptic spines decreases after you go to sleep. So actually you're pruning things that aren't important so you can kind of start over again. And so, has anybody in the room ever had trouble either falling asleep or staying asleep? So it turns out that about 80% of our population will say yes at some time. So basically, it can be situational, like stress or maybe a divorce or situational kind of thing that you kind of get over. But then there's some other things that really are more pathologic. One is called narcolepsy. Narcolepsy is a disease. We know that it's a disease where there's some abnormal wiring in the brain. And so the folks that have narcolepsy or cataplexy will just, for no reason, just fall asleep, just like that. And so if you're driving a car, you can imagine that's not a good thing. Or you can be standing up and you just fall asleep and fall down on the floor. So not a normal kind of thing. Sleepwalking, I think somebody mentioned sleepwalking. Sleepwalking is one of those sleep abnormalities where you're in a non-conscious state. And this has been a defense for murder because people say, well, I had no idea what I was doing. I was just walking around in my sleep, and I got the knife and I killed my spouse, or partner or something, So anyway, that's abnormal. Night terrors. Night terror. So again, you're at night when you're dreaming, you can have bad things that surface that you keep suppressed during the day. So this plays into depression. Depression, actually, if you look at the electroencephalogram, or if you actually look at the activity in the brain of somebody who is depressed, it is much higher than normal. So you'd think depression, you're dragging around, and you can't enjoy life. but actually your brain is going 100 miles an hour, okay? And you just basically, with the